Now let's look at not really light's relationship to matter per se, but light's relationship to atoms. Let's change this to atoms. So even though atoms are matter, we'll be a little bit more specific here. Atoms can acquire extra energy, but they must eventually release it. And when atoms emit energy, many times it's released in the form of electromagnetic radiation, often in the form of visible light. Now, when this light or electromagnetic radiation is emitted, it's not emitted in all colors, but only very specific wavelengths. In fact, the spectrum of wavelengths can be used to identify the element, and this is how elements in stars were first identified. Now over here we have a neon sign, and this right here is a tube filled with a gas, and when this gas is hooked up to something that zaps it with electricity, it emits a blue light. So let's look at what an emission spectrum is. What we do is we have a tube, like a light bulb, filled with a gas of a certain element, in this case hydrogen, and then it is connected with electrical electrodes and zapped with electricity. The atom gains energy from this electricity, and when it does, it then releases the energy in the form of electromagnetic radiation. And here we have the visible light spectrum, but only in very specific wavelengths. And this is what's known as a line spectrum, because the colors that are emitted just show up as lines. Now we have to put the light through a prism, which actually separates it. The light, I mean. So here would be a spectrum of pure white light. All the colors are emitted. Here are the emission spectrum of 3 different elements: hydrogen, helium, and neon. When hydrogen is electrified, it emits light of this wavelength. When helium is electrified, it emits light of different wavelengths. And when neon is electrified, and then it emits its energy as light, here are the wavelengths that are emitted by neon. Now, when this behavior was first observed, scientists were at a loss as to how to explain this, because they thought that the emission spectrum should look like this, just a continuous flow of energy. Another thing that puzzled scientists was the absorption spectrum. And here we have an absorption spectrum, an emission spectrum of hydrogen. Hydrogen absorbs electromagnetic radiation, but again, only very specific wavelengths. And it emits these wavelengths that are exactly the same. So why do certain elements have very specific wavelengths that are different from other elements, and why do they absorb and emit these wavelengths of very specific distance? And by the way, the units here are in nanometers. Scientists at the time understood that the atom had a nucleus of protons and neutrons, and that it had electrons that were further away from it. But they didn't have a detailed understanding of how the electrons were ordered. A scientist named Niels Bohr was a Danish scientist who eventually won the Nobel Prize for his work, developed a model of the atom to explain how the structure of the atom changes when it undergoes these energy transitions, the absorption and the emission of this electromagnetic radiation. Bohr's major idea was that the energy of the atom was what he called quantized, and this comes from Latin for quanta, which means packet, and that the amount of energy that an atom released or absorbed was related to the electron's position in the atom. And again, this term quantization means that the atom could have only very specific amounts of energy. The energy it could have was not continuous, but very specific. So here is an example of the hydrogen atom drawn out as a Bohr model. What Bohr came up with is that electrons traveled in what he called orbits around the nucleus. Now I can just draw 2 dimensions here. They weren't really going around in just 2 dimensions, they were going around in 3 dimensions. So if you can think of this as a sphere around the nucleus, more like shells than planetary orbits. And how close the electron was to the positively charged nucleus had a big impact on the energy of the electron. The closer an electron was to the nucleus, the more stable it was, and therefore the lower its energy. The further an electron was from the nucleus, the less stable it was, and therefore the higher its energy. And Bohr labeled these energy levels with integer numbers, 1, 2, 3, 4, 5, 6, etc. So we can liken the energy levels to a ladder. We can step on the first rung, or the second rung, or the third rung, but we can't step anywhere in between. So it is with the energy levels that electrons are allowed to have in an atom. They can have a very specific energy level, or another specific energy level, or another specific energy level, but no energy levels in between. So this is what we mean by this quantization. The energy of each orbital is characterized by an integer. The closer it is to the nucleus, the smaller it is. This would be the orbital that is closest to the nucleus. This would be next closest, next closest, next closest. This integer is known as a quantum number, and it's known as the principal quantum number, often symbolized by a lowercase letter n. Bohr theorized that when an atom gains an energy, the electron goes from a lower energy orbit to a higher one. So if an electron was here and it gained more energy, it would go up to another shell or another energy level. And it could be this one, or this one, or this one, or this one, just depended how much energy it actually absorbed. And then when an electron went from a higher orbit to a lower one, so from here down to here, or from here to here, then it emitted energy. And these very specific amounts of energy from here to here, or from here to here, are equal in energy and little packets of energy, a quantum of energy. And this energy is seen as electromagnetic radiation. So in this depiction, our straight lines are where the electron is going, and our wavy lines are energy. So when energy is absorbed by the electron, enough energy to take it from this first energy level to the third energy level, and then at some point, because it's in a higher energy level, the electron's got to go back down. It can go down directly to 1, or it can go down in steps. Here it's going down in the steps from 3 to 2, and as it goes down to a lower energy level, it is going to emit light or electromagnetic radiation.